All right. So knowing that we use telescopes, satellites, and computers, that's what we're going to spend today's lesson on. How do we study stars? So what I want to focus on today is specifically the telescope part, because as long as it is very cool about how satellites work and how the computers work and how they discover the astronomy, but the actual cool physics part that's unique to astronomy are the telescopes, because there are very few other fields of science that actually use telescopes to the same degree that astronomers do. So there are three classes of telescopes, really. The first type is what we call the hobby telescope. Hobby telescopes are for people who just want to look at the night sky, in their own backyard. These are typically a lot smaller. You can have them in your own home, right? You sometimes see a telescope like this, right? Like that or something, and there's, right? Those are like hobby type telescopes, the ones you can just mount in your backyard and look at the sky with. So a lot of people own hobby telescopes because, well, it's a hobby. People like looking at the stars. So out of these hobby telescopes, there are three types. You have the refractor, the reflector, and the cadioptric. Yeah, that's a hard word to pronounce. Cadioptric. Right. And then we have ground-based telescopes, which are the big telescopes, which we sometimes might refer to these as observatories. And these observatories are really massive. Sometimes they look like this, and they have an opening to look out into the sky with. Kind of like that. It's a really bad drawing, but I have other pictures. The ground-based telescopes are really big. They're the entire size of a building, and they have a massive mirror and telescope inside the ground inside that building. And of course, we have the ones that were mentioned before, which were space telescopes, which you can also call satellites, right? We can say satellites. And these telescopes are positioned in space. They're out there orbiting around the Earth. And the reason why we have them orbiting out there is because let's imagine the Earth, right? If we imagine the Earth is here, or let's make it bigger. Let's say this is the Earth, right? The Earth has an atmosphere, right? So this is the Earth's atmosphere. And if you put a telescope like right here, right, then all that light that comes from space hits the atmosphere and then gets filtered, right? It gets filtered out and it gets distorted by the atmosphere, because the atmosphere is filled with a lot of air and a lot of dust, and there's a lot of particles there. So if you really want to see light as it is before it hits the atmosphere, then you have to get above the atmosphere. And that's why we have so many telescopes out here. So that we can look at the light directly without having sunlight get in the way of it. Or not sunlight, the atmosphere get in the way of it. So that's why we have space telescopes. They're really expensive, really big, but they're worth it because we get a lot more clear pictures. All right, and now we're going to dive into the specifics. So here's the first type of refractor type of telescope, called the refractor. So these orange lines here are light. So that's light that's coming into the telescope. So what's saying here is that light travels in a straight line. So it's traveling, right? And then it hits our first lens, right? So this is a lens. So this type of lens is what we call a concave lens. And how a concave lens works is when light hits it, it hits it at a certain angle, right? This is the angle that it hits it at. And depending on that angle, it'll shoot through like this. Oh, messed it up. Like this, basically. Then exits at another angle. So this is how a concave lens distorts light. So we have light going straight, it hits it at a certain angle, it goes into the lens at a sharper angle like that. And then as it exits, it goes like that. So if we had the same light go from the bottom here and hit it, it also hits at that same angle. And then since the top light turns in like this way, and the bottom light will turn in like this way. And so that will go like that. And then it exits. So that's how a refractor, a concave lens works. So that's the first lens that it hits. The reason you have the second lens here is that if you look at this concave lens, right, you see how all the light concentrates at this one point. If we didn't have the second lens right here, then all that light that we got from the outside would be forced to, concentrate somewhere here. And obviously the telescope is this long. So you have to somehow extend that light, extend that focus point all the way back here. And that's what that second lens is doing. Making sure that that light gets focused where our eye is supposed to be. So that's why we have these two lenses here. The first lens being concave, which focuses the light, and the second lens, which is what we call convex, right? It has this type of shape, right? This is convex. It has that type of shape that allows the light to extend further into the telescope so that we can see it all the way over here and not here. So that's a refractor telescope. It takes light, it does what we call refracting, which is changing the angle of the light, like here, right? This is the refracting part. It changes the angle of the light so that it concentrates at a single point, and so your eyes can see it. So one of the, I guess, not drawbacks, but one of the features of a refractor type telescope is this long tube. All refractor telescopes have a very long tube. That's also why sometimes when, on pirate ships, you see a captain pull out their telescope and it kind of extends out, right? Because a refractor telescope is typically pretty long. So if you ever want to carry one around, it makes sense to be able to collapse it down. And so that's why pirate captains have that collapsible telescope. Those are refractor telescopes. All right, the next type is what we call a reflector telescope. A reflector telescope, well, has a lot of reflecting instead of refracting. It doesn't have any lens, instead it uses a mirror. So here we have a light coming through like this, right? Goes through, and then it hits the primary mirror. And if you look at the shape of the primary mirror, it has this convex type of shape. And that forces the light, when it hits it, to bounce inward, to kind of collapse inwards, and kind of focuses it. So this primary mirror focuses all that light that comes through onto the mirror and focuses it towards the secondary mirror. And it focuses towards the secondary mirror because that secondary mirror will then bounce it upwards straight into your, into your eye. So that's how this works. You'd have light coming through, and then hits the primary mirror, bounces, focuses onto the secondary mirror, which then bounces the light into your eye. Those are reflectors. So one question that I sometimes get is that, well, you have this giant secondary mirror right here in the center, right? Isn't that blocking all of this light? Right? How can you see anything in the center? Won't you just be blinded and you can't see what's in there? Well, that is certainly a concern. However, the thing is that light doesn't only travel like this. There sometimes is light coming from here. And light coming from there will bounce and get its way past. And hit like that. So light can take a lot of really fancy paths to get around this block in the center. So I agree that a lot of the light that does hit this block is blocked, but there's a lot of other light that can go around it. And as it goes around it, it can bounce, 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 like that. It'll bounce around the block and that'll never become an issue. So yeah, those are reflector type mirrors. One interesting thing about the reflector type mirror is that when you look at the image is actually inverted. Because if you look at right here, right, the bottom light, this is the light from the bottom, suddenly becomes the light at the top. Like this is top, this is bottom, this is bottom, this is top. So when it hits the secondary mirror, you can see how the light gets distorted and flipped around, right? This action right here flips the entire image around. So the images you get from reflector mirrors are actually upside down, which is kind of interesting. Yeah, those are reflectors. The third one is the really fancy name one, cadioptrics. Yeah, cadioptrics. The cadioptrics are a lot more complicated. So they use lenses and they use mirrors altogether. And the reason why they choose that is because if you look at the size of this cadiotropic, right, it's a lot shorter than the reflector mirror or the refractor, right? And the reason for that is because they compact all of that hardware into a really small bundle. As a result, the cadiotropic is a lot wider, but it's also a lot shorter. So as a result, it's easier to pack and it's a lot more portable because it's just so much smaller. But here's how it works. So you first enter into, the light enters through the corrector plate. So the corrector plate, what it does is, well, it corrects some of the distortion. One of the issues with cadiotropics is that if you don't have this corrector plate, then your image gets really blown up. Everything in the center is like kind of distorted. Everything in the background is kind of squished up. So without that this corrector plate, your image is going to be completely whack. So that's what the corrector plate is doing. It's not really focusing. It's not really trying to correct any. Sorry, it's not focusing. It's not trying to extend anything. It's just simply correcting the issues with the design of the cadiotropic. So it enters through the corrector plate. The light gets corrected a little bit. It hits the primary mirror, just like in our reflector telescope. And then it bounces onto then a secondary mirror, right? And from the secondary mirror, it then enters through the eyepiece into your eye. Right? The same thing happens at the bottom here. The bottom, the light travels, hits the mirror, bounces onto the secondary mirror, and focuses onto your eye. That is a cadiotropic mirror. So these are pretty cool because, well, they're a lot more complicated and they oftentimes tend to be a lot more expensive just because of how much more complicated this design is. So yeah, these are the most, these refractors are the least expensive. Reflectors are more expensive, and then cadiotropics are the most expensive out of our hobby type telescopes, at least. All right, so the next type of telescope are those big ground telescopes I was talking about. And I wanted to show this website because it has all the images in one place. All right, so let's take a look. So here are just 10 really big telescopes, ground-based telescopes that we have on Earth, right? So here's the first one that we have, which is what we call the LSST, or Large Synoptic Survey Telescope. So we can read a little bit about it. So this telescope cost $465 million. So it captures faint starry objects that change over time. So this type of telescope most likely is we call a radio or a radio or infrared telescope, because those are the best at looking at really faint starry objects. So if we look at the design of the LSST, you can see how here is that this is a reflector type telescope, right? Here you can see that giant mirror right here in the background, and here's that secondary mirror right here. So here, right there in the center, I don't know if you can see that, but that is our instrument. That's the instrument that actually measures how much light is there. So the light will come through, hit the mirror, hit the secondary mirror, and bounce its way into the instrument that captures light. And behind the instrument is get loaded onto some computer, and then the guy over here who's operating the telescope can see what the telescope is seeing. So that's pretty cool, right? So it still uses the same concepts as our hobby telescopes, but it's on a much larger scale. All right, so that's the LSST. All right, so here is our second one, which is called South African Large Telescope, or SALT, right? It's kind of funny. So here's the design. You have your giant mirror right here in the back, hits the primary mirror, and then goes on to what we call the optical payload. So in this case, there's no instrument in the center that's recording all the data. Instead, that's all up here in the optical payload. This is what's recording all the information. So it hits the primary mirror and gets concentrated onto here. So there are a lot of other pieces of this building. For example, what we call the mirror coating room, which is where you coat the mirror. So just in case sometimes the mirror isn't clean or whatever, you would have stuff here on how to make it cleaner. You have a control room, which is how you control it. You have a visiting tower, of course. The dome of where the telescope is actually stored in, and the structure, meaning, well, the structure that holds up this whole building. All right, so these ground observatories are like a really specialized building that we have. All right, and here is a really famous telescope. Is called the Keck observatories. So the Keck observatories there are two of them, and they are on summits of Hawaii's Mauna Kea. So these telescopes are really famous just because of how high they are, and because they're in Hawaii, there aren't many disturbances, because Hawaii is kind of on an island in the middle of nowhere, right? So it doesn't have a lot of disturbances from the rest of the world, which makes it so unique. So these telescopes are really big and really massive. As you can see, they're 33 feet in diameter and have 36 individual mirrors inside of it. So instead of having one giant mirror, you have one mirror that's divided into 36 parts. And each of these 36 parts can move individually to adjust on the focus of the mirror, which makes it really, really precise. So if there's anytime there's a issue with a focus, or there's something that the scientists believe isn't correct, they can adjust just one of the mirrors and make it better. Let's see what else. As said here, it studied Jupiter a lot, right? So it was observing some impacts on Jupiter, like a comet falling into Jupiter. It was looking at the dark spots, yeah, on Jupiter and stuff like that. So yeah, the Keck telescopes are pretty famous. And so here you see this giant strip running down the middle. That's actually a giant door. So when they want to actually use the telescope, they open up this giant door and it reveals the telescope. Let's actually take a look at it. I think it's pretty cool. Keck telescope. Yeah, like this. These are the Keck telescopes. That's pretty cool, right? And here is actually a pretty cool image. Well, this is kind of photoshopped, but the point is here that they're actually using lasers to take a look to find where they are in space. So by using this laser, they're able to track things a lot easier, like this, right? They both pointing their lasers at the same spot in the sky, and so therefore they get a lot brighter images, a lot more precise images of what they're trying to look at. So yeah, so this is why the Keck telescopes are so famous. They have some really cool technology. All right, let's move on. I'm not familiar with this one, the GTC, but we can read a little bit about it. So this one also contains 36 individual segments. Yeah, this one's not that crazy. This one, Arecibo. Arecibo is a really, really, really famous one. The reason for that is because you see this whole dish here, this giant hole in the ground. That whole thing is its mirror, a giant mirror in the ground. It's so big, it's actually 1,000 feet in diameter. So it is a massive telescope. And specifically, it's radio. It looks at radio signals, which is really, really, really faint, really, really weak signals. So that's why it has to be so big. If it wasn't so big, you wouldn't be able to figure out, you wouldn't be able to pick up on those radio signals. As it says, it's the largest single aperture ever constructed. Aperture meaning just like the size of the mirror. And after the light or radio waves hit this giant mirror, it bounces it up here. This kind of dome type thing over here, this semicircle or semi-dome. That's the instrument. The instrument is held up by these 3 giant poles. These poles are just dangling this dome over the mirror, and that's how it's been receiving information or radio signals. However, something really tragic happened over quarantine, where Arecibo was actually destroyed. There's an earthquake in Puerto Rico, Arecibo Observatory collapse, and as a result, an earthquake happened and it caused the whole thing to collapse. Look, here's a before picture. It was dangling completely fine, and here's the afterwards. Here's some more pictures. You can see the entirety of the dish is completely ruined. The towers have fallen. Yeah. So that was pretty sad that we lost such a big and impressive telescope. But soon we're gonna, yeah, hopefully we'll have a replacement up in the next couple decades. All right, so here's the ALMA telescopes. So this is the Atacama Large Millimeter Array. So instead of just being one telescope, this is actually a whole series of telescopes. So 66 total telescopes all in this one area. These 66 telescopes all point in the same direction, and they all study the same thing. But the reason why you have 66 of them is that by having so many different telescopes in slightly different areas, you get a really precise image of what you're looking at. So basically, you're using 66 telescopes to pretend you're one telescope. And that's what they're trying to do here. Yeah. So they are also what we call radio telescopes. That's why it has to be so big, right? The Arecibo is 1,000 feet in diameter, but not everyone can build that. So instead, we build a bunch of telescopes that add up to that area. So it's also a radio telescope. And this allows what we call the ray to look into the dark ages, what we talked about last class, right? Only just about up to 300,000 years after the Big Bang. So that's a really long time ago. All right. Oh, this is a really nice shot, actually. This is the Giant Magellan Telescope. So as you can see, these are very expensive, $1.1 billion, right? So this Magellan telescope is 80 feet in diameter and has 7 segments. And you can see each of these are an individual mirror. So this is also a reflector type mirror because the light hits each one of these mirrors. It gets focused onto the secondary mirrors. And if you really look and focus in there, you can see how there are actually 7 individual mirrors. Each one of these mirrors corresponds to a smaller secondary mirror up here, and then that gets focused down through the center into the instruments, the optical instruments. That's pretty cool. So let's see. Large main mirror would dwarf current generation telescopes and produce images 10 times sharper than the Hubble Space Telescope. So what this is saying is that this main mirror is so big that it's actually a lot better than the Hubble Space Telescope, right? But the issue is that it's so much easier to build giant mirrors on Earth than it is to send them into space, right? So that's what makes space telescopes so difficult. All right, here's another telescope, the 30-meter telescope. So this is a massive $1.4 billion telescope, which is even bigger than the Magellan telescope and 98 feet in diameter. Like this thing is absolutely massive, right? So this type of telescope is what we call an optical telescope, meaning that it's look at visible light. So it will looks at visible light and then takes pictures of it. So yeah, that's the 30-meter telescope, absolutely massive. Get some really nice crisp images. So these are pretty funny. These are the square kilometer array. So these are also radio telescopes, but these are also kind of different, right? We've seen the we're here, right? The large millimeter array, which is 66 in total. The sub-millimeter array has 30 of them, or 150 stations. So there are 150 of these spread out. As you can see, look at them all in the background, right? All the same thing. There's one here, all over here, right? So that is this array. What just happened? Here we go. So these are interesting in that you can see how their sensors are actually all the way over here, right? They're not in the center of the dish. So this kind of gets around that issue that we had with other reflectors. We have that giant block in the center blocking a lot of signal. So this kind of gets around that by placing the optical instruments towards the side. So when light hits it, it gets bounced over here instead of into the center. You can also kind of see how the mount for all of these telescopes are kind of off center. And that's to adjust for the fact that this optical sensor is off center as well. So that's the square kilometer array, also a super massive, impressive radio array. All right, what just happened? All right, last one. And here is the European Extremely Large Telescope. A very creative name, isn't it? Extremely large. So here's it's similar to the Keck telescopes, where you can see there's a giant dome and the dome opens up. to reveal a giant reflecting mirror. So this, how big is it? Well, it's 138 foot, so absolutely massive, right? It's made of almost 1,000 individual segments. So same thing here, you can individually adjust each of these segments to create a crisper image. So yeah, that is the extremely large telescope. So as you can see, we have a lot of variety in our ground-based telescopes, and there are obviously a lot more than I'm showing here. These are just the biggest ones that we have on Earth. I don't know if you guys knew, but we actually have one really close to us, down in Baltimore. There's actually a small observatory, and I actually got to see Jupiter through that telescope once. So that was a pretty cool experience. All right, and now on to the space telescopes. So before I explain some space telescopes, I'll just take a look at some of them. Right, so Hubble Space Telescope. So our space telescopes are really some of our greatest achievements as humanity. We basically sent out a telescope into space, right? So here are just some pictures. So here's a picture of the telescope being opened up, right? You can see how there's this flap up here that opens up whenever Hubble wants to take a picture. So here's a flap opened up, and you can see, you almost see the sensors in the back, but you can see how light enters through here, it gets reflected and then sent back down, right? So Hubble is a reflector type telescope. So here's Hubble going around. You can see how it has this antenna dish at the top, which is meant to beam things back onto Earth. You have your solar panels on the sides. You have all your equipment and sensors down here in the back. Here's here's like a schematic of it. You see the solar panels, the cameras, primary mirror in the back, aperture door, the secondary mirror, which I was talking about, right? Yeah, you got an idea for what Hubble looks like, right? Here's a GIF of it. Pretty cool. And look how small the astronauts are. So these are some astronauts. This was when the Hubble Space Telescope was first deployed. So it was deployed on our Discovery space shuttle. And when it was deployed, it used this giant arm to attach to the Hubble Space Telescope and kind of drag it out and drop it into space. So these are the astronauts who are helping work on it. So you can see how big the space telescope is, right? And that's just a person. That's pretty massive. And we sent that all the way into space. So that's the Hubble Space Telescope. It has taken some incredibly beautiful pictures. So here is what we call the Hubble Space extra deep, ultra deep field. So basically what the Hubble Space Telescope did was scientists just pointed this telescope at somewhere, the darkest spot in the sky. They said, you know, we only see so many stars with our current telescopes, right? What is this dark patch in the middle? There seem to be no stars here. So they pointed the Hubble Space Telescope at it, expecting not to see anything at all. They didn't think there'd be any stars there, but instead it took a picture like this. The real picture looks like this, but each one of these individual blobs and smudges, each one of these dots is actually a galaxy. So some of the galaxies are very clear, like this galaxy is really clear, this galaxy is pretty clear. But even those faint dots all the way in the background, those are also galaxies. So that really surprised scientists because they didn't think that there were this many galaxies, and that completely changed how astronomers thought about our universe. So that's pretty impactful. Some images that we've seen are this one. This is what we call Horsehead Nebula, which kind of makes sense because that kind of looks like a horse's head. But this is also a really nice picture that Hubble has taken before. So yeah, Hubble has taken a lot of really crazy pictures throughout its lifetime. So yeah, Hubble telescope is really impressive. But so how does the Hubble Space Telescope even work? Well, here is how it works, right? It's very similar to all the reflector type mirrors we've seen before, except this one is more like a catiatropic, right? So it comes through, it hits the primary mirror, which is, kind of split apart, right? There are two actually primary mirrors, hits the incoming light, hits the secondary mirror here and then bounces through the center, right? So this is more like a catiatropic type. So in the back here are all the sensors and that giant box there, all the cameras and optical instruments in the back. And this is the aperture door, which opens up whenever you need to take a picture. And when you don't, you close it up. But yeah, this is the Hubble. So there are some more specific instruments here, or like the radial scientific instruments or fine guidance sensor. But all these things do is just make sure that the picture that Hubble takes is very crisp and very clear and in focus. That's the Hubble Space Telescope. Some other pretty cool ones that we've seen before that I really like are here is the Chandra Space Telescope. So the Chandra Space Telescope, I should clarify before that the Hubble Space Telescope takes pictures of optical light. So what does optical mean? Optical means the light that we can see, right? The greens, the blues, yellows, everything, right? However, Hubble isn't very good at looking at infrared, radio, or higher energy light like ultraviolet light, X-ray light, or gamma ray light. So those types of light Hubble can't really do a good job of, and that's why we have other space telescopes to help do the job for us. So here is Chandra Space Telescope. And Chandra Space Telescope is pretty interesting. So Chandra Space Telescope does not have a refractor, it doesn't have a lens, it doesn't have a reflector, it doesn't have a primary mirror, so to say. What it does have are these things, these sheets of mirrors, basically. These are basically a cone, like a cylinder of a mirror. To be specific, they're called paraboloids. But it's kind of like a sheet of a mirror, like a circle, like a cylinder of it, like that. And they have it pointed towards the mirror. The reason for that is because X-ray light is super high energy. So optical light might be about this energetic, right? But X-ray light is like this energetic. So there's a lot more energy inside X-rays than there are in optical light or invisible light. So as a result, if we tried to put a mirror in the back like this or something like that and had the light try to bounce at it, the X-ray light would actually pass right through it. It's just that powerful. One analogy that I can give is that imagine if you took like a piece of paper or something like that, or like a piece of metal and tried to shoot a bullet at it. Well, what would happen? The bullet would go through the metal, right? If it's like a piece of tinfoil, right? It would just go straight through. However, if you angled that light, like kind of like this, if you angled that piece of metal like this, instead, the bullet would just ricochet off. So it would come through like that and just ricochet off. Instead of breaking the piece of metal, you now can have the bullet ricochet off the metal instead. So that's what all these mirrors are doing. It takes in all that light and ricochets it off the first mirror, ricochets it off the second mirror, and then into the sensor. It does that because it can't have that single primary mirror. Otherwise, you wouldn't be able to reflect any light. You would just break the mirror, or it would pass right through it. So that's what this diagram is showing here. And that's why the Chandra Space Telescope has such an interesting opening, right? When it also has the same aperture door that opens up when it ever wants to take a picture, but instead you have these really interesting looking slits where the light has to go through, right? That's what makes the Chandra Telescope kind of cool. Yeah. And then as you can see, it bounces here, it bounces in another mirror here, and then goes all the way back here to the sensor box, and that's where the camera is. So that is Chandra. And obviously also solar panels on the sides. Now we come to the James Webb Telescope. So the James Webb Telescope actually is not in space yet. The James Webb Telescope was initially created sometime in 1990, I think, and they wanted to originally launch it in 2003. However, because they kept on having delays and they kept on having more issues that they had to fix, the current launch date is actually sometime this year. So the James Webb Telescope is supposed to be the biggest telescope we've sent into space yet. You see how all these individual mirrors here. And just for scale, I feel like it's a good idea to show you guys a picture of what James Webb actually looks like. James Webb Space Telescope. I don't know if you guys knew, but the James Webb Space Telescope was actually inside Maryland. It was in Maryland for the longest time, inside our own Goddard Space Center down in Maryland. So let's see if we can get some people in scale. There we go. So here's a person, and that's how big the aperture, that's how big the mirror is by itself. All right, so that's massive. Here's a mirror laid down flat and all those people standing around it. Here's the mirror folded back. Right, they fold it back, and then here's it extended. Right here, the left side of the mirror is currently, they're testing the folding out process. And the reason they have to fold it is because they have to fit it inside a rocket, right? So that's why they have to fold it back. And then as it opens up, it'll become fully deployed. So yeah, this is how big the telescope is. Very massive. So here's what's really cool about it. Well, the James Webb Telescope has 18 beryllium-coated mirrors. So Be is the fourth lightest element that we have in existence. And the reason why we chose that is because beryllium is incredibly reflective, and that's what gives it this kind of goldish color, goldish look. It's 21 feet in diameter, so not nearly as big as our what you call ground-based telescopes, but this is going to be the biggest telescope that we've ever sent out into space. So because of how big it is, it has to be very sensitive, right? And it's so sensitive that it can only operate at negative 223 degrees Celsius. That's how cold the James Webb has to be. And that's why it has all this stuff underneath it. All this stuff underneath is what we call the sun shield. The sun shield is sunlight is going to be hitting the James Webb Telescope like this. So if you imagine the sun is right here, the James Webb is actually like this, with the telescope over here and like that. So this is the sun shining, shining, shining. The James Webb Telescope is actually going to be sideways like that, facing away from the sun at all times to make sure that direct sunlight never hits it. So as sunlight hits each one of these sun shields, you decrease in temperature, right? So this sun shield right here is going to be super hot. This is going to be a lot less hot, way less hot, way less hot. And by having all of these different layers in between the James Webb and the James Webb Telescope and the sun, you can actually reach those negative 223 degrees Celsius temperatures. So it's pretty crazy. Here, you can see a glimpse of the solar panels that are used to power the James Webb Telescope. They're obviously on the bottom of the telescope because, well, how else are you going to take in the sun, right? So sunlight hits it, and that's what powers the telescope. Some other stuff about the James Webb, I guess. It's also a reflector type telescope. You can see the mirrors are all here. It bounces them all onto the secondary mirror up here, and from there it bounces onto our instruments right there. So the James Webb Telescope is meant to look at infrared and radio signals, because that's why you have super big telescopes. Those are really good at looking at radio and infrared signals and microwave signals. So that's what the James Webb is specified for. That's why it has such a weird looking optical instrument, because it's only looking at radio. So yeah, that's the James Webb Telescope. Hopefully it'll be able to launch this year, and hopefully it's going to be really successful. Otherwise, it's going to be kind of sad that we spent so much money and time on this telescope and it fails. So I'm pretty excited for it. All right, so we can watch this video. So this is a video I showed on our very first lesson, but I think it's still an interesting video to watch. This is a good recap of what we learned so far. Let's see, TED Ed, how do we study stars? All right, that's good.
Are they from Earth? The city sky is frankly rather boring. If you look up at the patches of murk between buildings, you might be able to pick out the Big Dipper, or perhaps Orion's Belt. But hold on, look at that murky patch again, and hold out your thumb. How many stars do you think are behind it? 10? 20? Guess again. If you looked at that thumbnail-sized patch of sky with the Hubble Space Telescope, instead of points of light, you'd see smudges. These aren't stars. They're galaxies, just like our Milky Way, cities of billions of stars, and more than 1,000 of them are hidden behind your thumb. The universe is bigger than you can see from the city, and even bigger than the starry sky you can see from the countryside. This is the universe as astrophysicists see it, with more stars than all the grains of sand on Earth. By staring up at the stars at night, you've taken part in the oldest science in human history. The study of the heavens is older than navigation, agriculture, perhaps even language itself. Yet unlike other sciences, astronomy is purely observational. We cannot control the parameters of our experiments from lab benches. Our best technology can send man to the moon and probes to the edge of the solar system. But these distances are vanishingly small compared to the yawning gulfs between stars. So how can we know so much about other galaxies, what they're made of, how many there are, or that they're even there at all? Well, we can start with the first thing we see when we look up at night, the stars. What we are trying to learn is their properties. What are they made of? How hot are they? How massive? How old? How far are they from Earth? And believe it or not, we can learn all of these things simply from the light shining in the sky. We can decipher one kind of stellar message by turning starlight into rainbows. When you look at a rainbow on Earth, you're really looking at light from our sun being scattered through water droplets in the atmosphere into all the different wavelengths that make it up. And when we study the light from other stars, we can create rainbows on demand using not water droplets, but other specific instruments that disperse light. When we look at the scattered light from our sun, we see something strange. Dark lines in our rainbow. These lines are the characteristic fingerprints of atoms. Each type of atom in the solar atmosphere soaks up light at specific wavelengths, and the amount of absorption depends on how many of these atoms there are. So by observing how much light is missing at these characteristic wavelengths, we can tell not only what elements are in the sun's atmosphere, but even their concentrations. And the same idea can be applied to study other stars. Make a spectral rainbow, see what's missing, and figure out which elements are present. Bingo! Now you know what stars are made of. But we aren't restricted to just the wavelengths that our eyes perceive. Consider radio waves. Yes, they can bring the Billboard Top 100 to your car, but they can also travel almost unimpeded through space. Because they've come so far, radio waves can tell us the very early history of the universe, from just a few thousand years after the Big Bang. We can also study the infrared light emitted by colder objects like the gas and dust clouds in space, and the ultraviolet light from the hot stars recently born from those clouds. Studying different wavelengths not only gives us a more complete picture of any single object, but also different views of the universe. For this reason, astrophysicists use several different kinds of telescopes, covering the spectrum from the infrared to the ultraviolet to the X-ray, from giant radio dishes to giant silver mirrors to space satellites detecting light that would be otherwise blocked by the Earth's atmosphere. Astrophysicists don't just see the billions of stars among the billions of galaxies in the universe. They hear, feel, and sense them through many channels, each revealing a different story. But it all begins with light, the kind we can see and the kind we can't. Want to know the secrets of the universe? Just follow the light.
All right, so in the TED Talk, it kind of explained, everything comes through light, and that's why we use telescopes, right? Because it tells us so much about different stars just by studying light. One of the big concepts that they touched upon is emission spectrum, right? How do we know so much about the composition of stars, not just how hot or how big they are? So here is a little bit a diagram of how that works, kind of. So through a slit, basically, we look at light through a really thin slit, and then you can what we call diffract that light. When you diffract that light, you split it into its different pieces, basically. Like the same way that, as the video explained, sunlight raindrops diffract sunlight and create rainbows. The same thing you can do with like a glass prism, right? And by doing that, you get all these different distinctive bands on, these distinctive bands of color. And each of these distinctive bands, are distinct towards a very specific atom. Each atom has a very different signature, and that's what we call an emission spectrum. So if we ever saw a line here, 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 and here, we know immediately that is hydrogen, without a doubt. Every single hydrogen molecule in the universe has the exact same emission spectrum. That's what we mean by it's kind of its fingerprint. So if we look at all these different gases, basically, each one of them have a very distinctive color, right? And that's because, they have a very different emission spectrum. So you can see helium is kind of a purple, a kind of pinkish, neon, really nice and bright red, argon, a deep violet, krypton, a kind of clear blue maybe, and xenon, a really distinctive like ocean type blue. So yeah, that's what emission spectrums were. And the last thing you talked about is how looking at all these different wavelengths of light give us a lot of information about the objects that we're looking at, right? So here we have visible light, right? You see everything in our rainbow is visible light. That is a very narrow band of the vast energies of light that do exist. So you have stuff that's really, really low energy, like radio waves and microwaves and infrared. So let's take a look at what each of these types of light give us. So radio waves are incredibly cold, right? So a lot colder compared to everything else, at least. And so this gives us ideas about cold gas. They reveal regions of cool gas, cool enough for CO2 molecules to exist. So it focuses on really big atoms such as carbon dioxide. So this is a picture of a galaxy, and you can see all the concentrations of where that CO2 is. Moving to something a bit hotter, we have our infrared light. Infrared light shows us the small, cooler red stars that make up most of the galaxy. So this is our best bet on how we can pick up brown dwarfs, how we can pick up main sequence stars. We look at infrared light because that type of light is the most dominant in those colder stars. Then we have optical light, right? Things that like the size of our sun, right? We are perceived most optical light because our sun is like optical. It's the same temperature as that. So that's why we like everything in optical light. That's why it's so colorful to us. Um, then if we want to see things even bigger than our sun, even more hot, even more powerful, we have to look at ultraviolet, right? That shows the new hot blue stars, stars that just formed, and these protostars. That's what we're going to see using ultraviolet. Then getting even hotter than that, we have X-ray. X-ray is emitted by the hottest regions in galaxies where they say atoms are being ionized, right? Ionized meaning they're basically being stripped of their electrons. The same thing that kind of happens in the sun's core. So whenever these atoms being ionized, that shows there's a lot of super hot activity going on. And that kind of makes sense that in the center of a galaxy where you have supermassive black holes and a lot of crunching and a super high gravity, then it makes sense that we would see a lot of X-rays there. So yeah, by looking at different types of rays, different types of light, we get a completely different picture of our universe. And by looking at them through our different telescopes, through your ground telescopes or space telescopes, we learn a lot and continue to learn a lot about our universe. So with that, that's the conclusion of today's class and conclusion of the astronomy class in general. I hope you guys learned a lot about, well, at least learned something about astronomy, how we study it, about the evolution of stars, evolution of galaxies, and the creation and future of our universe. I hope you guys enjoyed, and thank you for attending.
Bye.
Bye.